Good afternoon. My name is Ochirov, and I'm from the Institute for Problems in Mechanics of the Russian Academy of Science. Today, I would like to present a methodology of constructing complete analytical asymptotic expressions that describe the large-scale dynamics and fine structure of periodic flows in continuous media. Using the example of an unbounded, compressible atmosphere with a non-uniform temperature distribution. The methodology is based on the works of Ali Hassan Naifeh, excellently presented in his book Introduction to Perturbation Techniques. Observations show that all fluids in nature are heterogeneous and structured. Density in the atmosphere and ocean is not constant and varies with height. Thin layers and filaments, ligaments, voids are observed between relatively homogeneous strata. These thin layers ligaments are characterized by high density gradients and determine the structure of the fluid and the flows in fluids. If we consider the parameters and scales of a continuous fluid, we can see that liquids and gases are characterized by a large set of intrinsic parameters that determine temporal and spatial scales. These intrinsic scales vary over a wide range and determine the characteristic times and lengths of the occurring processes. We consider a two-dimensional compressible viscous stratified unbounded fluid with a non-uniform temperature distribution. The problem is to calculate the dispersion characteristics of flows propagating in such medium. The mathematical formulation is shown on the slide and consists of the momentum transport equation, Navier-Stokes equation, the mass conservation equation, continuity equation, the heat conduction equation, and a linearized equation of state for a chemically homogeneous fluid. The problem is linearized in a standard way. For periodic flows in the form of harmonic perturbations with a real and positive definite frequency, the mathematical formulation is written as follows. So, substituting the assumed form of solution into the system of equations, it leads us to a system of algebraic equations for amplitude factors. Compatibility condition, the equation of motion, the equation of motion can be readily obtained in a spectral form, like it presented in this slide. And for an atmosphere linear stratified in temperature, the spectral equation of motion is written as follows. The frequency omega is positive definite, while the components of the wave vector kx and kz can be complex and determine periodic spatial motion and spatial damping. This equation is of the same order as the rank of the system of fluid motion equations. The order is 6 in this system. Anisotropy is observed along the vertical coordinate z, so the solution is sought for the wave vector component kz, like it presented in this slide. To obtain analytical asymptotic solutions, it is convenient to consider the spectral equation in dimensionless form. We choose the intrinsic scales of the problem as the parameter for non-disdimensionalization. For these parameters, we will take the buoyancy frequency and the viscous stratification wave scale. This naturally yields dimensionless parameters characterizing the ratios of the intrinsic scales. Three small parameters appear in the problem. These parameters are theta is a temperature parameter, Frad in -1 degree, and the small parameter epsilon. The methodology for obtaining asymptotic solutions involved sequential expansions of the problem in terms of these small parameters according to their magnitude. So, typical magnitude for these parameters obtained in this slide for liquid with characteristic of water and with characteristic of air. The smallest parameter, 1 divided to fluid, is the inverse fluid number. With respect to this number, the equation is regularly perturbed and the solution is sought in the form of regular expansions. A system of equations is constructed, the sequential solution of which yields roots with a given accuracy. The first equation of the system is expanded in a series with respect to the following small parameters. The fact with respect to the small temperature parameter, the equation is also regularly perturbed and the solution method is similar. However, with respect to the parameter epsilon, the equation turns out to be singularly perturbed. The fact is that the small parameter multiplies the highest order term, and the solution requires the application of combined regular and singular methods of solving equations. Using regular expansions yields one pair of solutions describing waves. The equation is of the sixth order. Two more pairs of solution can be obtained using singular expansions. They describe ligaments, fine structural components of flows manifested as high gradient layers and thin ligament filament and thin filaments. Yes. When we taking the limiting transitions, the solutions of the problem transform into waves and ligaments in a homogeneous atmosphere, and in an isothermal atmosphere, one of the ligaments disappears. In this approximation, the rank of the system of equation decreases, leading to the loss of qualitative ligament responsible for heat transfer. In an ideal fluid, the regular solutions reduce to classical expressions for acoustic waves, while the singular solutions vanish. An ideal fluid qualitatively describes a fluid devoid of structure. Since all fluids in nature are structured, an ideal fluid represents a mathematical abstraction, and this model is only mathematical. It is we can't describe fluids in nature with this model. When modeling flows of liquids and gases, it is necessary to base the work on the system of fundamental equations of fluid mechanics. When simplifications and approximations are made, the order of the system of equation decreases and qualitatively different solutions are lost. In conclusion, I would like to say that the works of Ali Hassan Naifeh, when the methodology is applied correctly, allow obtaining complete solutions of dispersion relations, describing both large-scale waves and fine structural ligaments of various natures. So the conclusions are constructed in this slide, and I want to thank you for your attention. Thank you.